Welcome to the deep dive. Today, we're tackling a really big question. What are the most promising paths right now towards building a truly powerful quantum computer?
Yeah, it's a huge topic.
And to get into it, we're diving into two major recent stories. You've probably heard about them. Google's Willow processor and Microsoft's Madrona 1 chip.
Two very different approaches.
Exactly. So consider this your shortcut to understanding, what's really significant about these cutting-edge efforts.
Right. You want to know what's important, what the actual advancements are beyond the headlines. And that's pretty much our mission here. We've sifted through the latest research, the papers, the commentary, to bring you the core insights on these, well, fundamentally different strategies.
So we'll look at Google's strategy first, basically refining their existing superconducting tech. And they've got some, frankly, really impressive results in error correction we need to talk about. Then we'll contrast that with Microsoft's path, which is much more, well, radical, I suppose. Pursuing these topological qubits, huge potential, but also facing some significant hurdles.
Big hurdles. We've pulled together a range of sources, trying to give you a clear picture of both.
Okay.
What hits you immediately, though, is just how different the philosophies are. Google is, making steady, measurable progress, improving a technology they already know quite well.
Incremental, but significant.
Right. Whereas Microsoft is really aiming for a whole new foundation. A moonshot, almost.
Okay, let's start with Google then. Unpack their progress with the Willow processor. So this is their newest superconducting quantum computer, building on what they did with Sycamore.
That's right. It's a 105-qubit architecture. Uses superconducting transmon qubits, like Sycamore, arranged in a 2D grid, a lattice.
And it must be a big help that they have their own dedicated fab facility in Santa Barbara, right?
Right.
For building these things.
Oh, absolutely. A huge advantage. It lets them iterate much faster, tweak designs, optimize things. That rapid feedback loop is crucial.
Makes sense. Now, comparing Willow to the older Sycamore chip, what are the key improvements? They talk about coherence first.
Yeah, coherence is key. It's basically how long the qubit can, hold on to its quantum state before it just dissipates.
Yeah.
And their T1 times, that's the main measure, they've improved roughly 5-fold, which is a big jump.
5-fold. Wow.
Okay.
So from what to what?
Well, Sycamore was around, say, 20 microseconds. Willow was averaging. Depends on the specific chip within the processor, but between 68 and 98 microseconds. So, yeah, a substantial improvement.
And why is that longer coherence time so important?
Well, it's fundamental. The longer your qubit stays quantum, the more complex calculations you can run, the deeper the circuits can be, before noise and decoherence just overwhelm the signal. It gives you more time to actually do something.
Okay. And what about the accuracy of the operations, the gate fidelity?
Also improved. Roughly a factor of 2 better across the board compared to the last generation.
So fewer errors when they actually manipulate the qubits?
Exactly. Fewer errors per gate. Things like their 2-qubit CZ gate errors are down to around 0.33% on average on one part of the chip, even lower for ISWAP-like gates on another part. Single qubit errors are tiny, like 0.035%. Still not perfect, nowhere near fault-tolerant levels yet, but definitely state-of-the-art for this scale.
Right. Still a long way from the 6 nines of reliability you need for fault tolerance, but heading in the right direction.
Precisely. Fewer errors at that physical level make everything else easier, especially the error correction.
And the layout. You mentioned a 2D grid. How are they connected?
Yeah, typically each qubit is connected to 4 neighbors. The average across the chip is about 3.47 connections per qubit. And that connectivity is really designed specifically for implementing these 2D surface codes for error correction.
Okay, so the physical layout is built for the error correction scheme.
That's the fascinating part about Google's approach here. It's very holistic. System-level engineering. They're not just trying to build the world's best qubit in isolation.
Right.
They're co-optimizing everything, the qubits themselves, how they're connected, the control signals, the readout, all aimed at making the quantum error correction perform as well as possible.
Which brings us neatly to the big news, really. Their quantum error correction results using these surface codes. Can you maybe give us the quick version of how surface codes work?
Sure. So imagine you want to protect one fragile piece of quantum information that's your logical qubit. Instead of storing it on one physical qubit, you spread it out. You encode it across a grid of many physical qubits.
Like a checkerboard.
Sort of, yeah. Some qubits on the grid hold the actual data in a distributed way. Others, called measure qubits, are constantly checked for errors. They look for flips or phase changes in their neighbors.
And they can detect errors without actually measuring and thus destroying, the data qubit itself.
That's the clever part. They detect the syndrome of the error, like where it happened and what type it was, without revealing the underlying quantum state. And a key idea here is code distance, usually called D.
Okay, code distance. What's that?
Think of it like the size of the protective grid. A distance 3 code might be like a 3x3 patch of qubits working together. A distance 5 code uses a larger 5x5 patch. More qubits, more redundancy.
Right, like having more spotters when someone's lifting a heavy weight.
Exactly. More neighbors checking for errors means it can detect and potentially correct more complex errors. A higher distance code should be better protected.
And the really exciting news from Willow is that they showed this actually works.
Yes, that's the below threshold result. They showed that as they increase the code distance going from D3 to D5 and even up to D7 on a related chip, the probability of an error happening to the logical qubit per cycle actually went down.
It got better as the code got bigger.
Right. By a factor of about 2.14 each time they increase the distance. This is like the first really convincing experimental proof that the whole surface code theory holds up in practice at this scale. It validates decades of theoretical work.
So it's not just theory anymore. It's an engineering pathway.
It shifts it firmly into an engineering challenge, yeah. How do we scale this? How do we make the physical parts even better? But the principle works.
And there was more, right? Something about beyond break-in.
Yeah, that's also huge. They found that their logical qubit, the one protected by the largest code, the D7-1, had a coherence lifetime of 291 microseconds.
Okay. And how does that compare to the individual physical qubits?
That's the point. It's more than double the lifetime of their very best individual physical qubit on that chip and over 3 times the median lifetime.
Whoa. So the error correction isn't just fixing errors. It's actively making the quantum information last longer than the components it's made from.
Exactly. It's preserving the quantum state better than any single physical qubit could alone. That's beyond break even. The overhead is paying off in actual improved performance.
That really shows the power of being below threshold, doesn't it?
It does. Think about it. They got maybe a 2-fold improvement in their physical gate fidelities compared to Sycamore. But because they're below threshold with the error correction, that translated into a 20-fold reduction in the logical error rate.
Wow.
It shows that once your physical qubits are good enough, even small improvements in them can give you exponential gains in the logical qubit's performance through the error correction.
And they're using some pretty sophisticated software behind the scenes to handle all this error detection and correction, right? Machine learning and stuff.
Yeah, decoding the error syndrome, figuring out what correction to apply based on the measurements is computationally hard itself, especially doing it fast enough. They're using ML, graph algorithms, reinforcement learning, cutting-edge classical computing to support the quantum processor.
But it's not all solved yet. They mentioned challenges.
No, definitely not. They observed what's called an error floor in some simpler experiments, where making the code bigger stopped helping beyond a certain point. This might be due to more complex errors, like bursts of errors, or errors that are correlated across qubits, which the basic surface code isn't designed for.
Ah, okay. So reality is more complex than the simple models.
Often is. And also, doing that decoding in real time on the microsecond timescales needed is still a massive challenge as things scale up.
Okay. So error correction is a huge part of the Willow story, but they also used it for one of those benchmark tests, right? Random circuit sampling.
They did, yeah, using a configuration with 103 qubits. RCS is basically running a complex random sequence of quantum gates. It's designed to be something that quantum computers should be good at, but classical computers find incredibly hard to simulate.
It's their quantum supremacy benchmark.
Exactly. It's less about solving a useful problem and more about demonstrating the raw power of the quantum hardware compared to classical simulation.
And the result.
Willow ran a specific RCS instance, 103 qubits, 40 layers deep in under 5 minutes.
Okay. And the classical comparison.
Google estimates that simulating the same thing on Frontier, currently the world's fastest supercomputer, would take. Well, the number they give is around 10 to the power of 25 years.
10, followed by 25 zeros. Years.
Yeah. It's a number that, doesn't really mean much practically, except that it's effectively impossible classically.
So this reinforces their 2019 claim pretty strongly.
It does, and they argue the gap is widening significantly. Nevin from Google talked about the classical cost growing like a double exponential compared to the quantum resources needed. The quantum computer is pulling away fast on this specific task.
But we need that caveat again, right? This is quantum supremacy on a specific, maybe not very useful task, not necessarily quantum advantage on a real-world problem.
Absolutely crucial distinction. RCS is a great stress test for the hardware. It shows impressive quantum complexity, but nobody needs the answer to a random circuit sampling problem. Quantum advantage is the goal. Beating classical computers on something valuable: drug discovery, material science, optimization.
Got it. So if we summarize the key Willow stats,
Yeah.
105 qubits, decent connectivity, much better coherence times, improved gate fidelities.
And crucially, that demonstrated error correction, showing the surface code works, suppresses errors by 20x below threshold, gets logical coherence beyond physical. That factor of 2.14 is a key metric.
Right. But that logical error rate around 0.14% per cycle is still way off fault tolerance, yeah.
Oh, orders and orders of magnitude. We need error rates down in the 10 error-grease to 10 error range for fault tolerance. So huge progress, but the mountain ahead is still enormous.
So what's Google's plan? What's the roadmap look like after this?
Well, these QEC results hit their milestone 2, which was demonstrating error correction. Milestone 3 is the next big one, building a long-lived logical qubit, targeting an error rate of 10 error, so 1 error per million operations.
10 to the minus 6. How many physical qubits do they think that will take?
Based on that O factor of 2.14 getting down to 10 error, they estimate needing maybe a distance 17 code.
Distance 17.
Which translates roughly to something like 1,400 or 1,500 physical qubits, just to make one logical qubit at that quality.
Wow. Okay, that really drives home the scaling challenge.
It absolutely does.
Yeah.
And that's just for one logical qubit. A useful fault-tolerant computer will need hundreds or thousands of logical qubits.
And beyond milestone 3?
Milestones 4 and 5 involve performing logical gate operations, and then milestone 6 is the big one. The million physical qubit fault-tolerant quantum computer targeting those ultra-low 10 or so error rates.
So still needs continued improvements in the physical qubits, maybe better codes, faster decoding, massive infrastructure.
All of the above. It's a relentless engineering march. Most experts still think large-scale fault tolerance is maybe 10, 15 years out.
But we might see useful niche applications sooner, quantum advantage in the next few years.
That's the hope. Maybe for specific chemistry simulations or optimization problems, using these noisy intermediate-scale quantum NISQ devices, maybe with some error mitigation, if not full correction, within maybe 2 to 5 years, it's possible.
Okay, so Google's path is clear. Engineering, scaling, refining. Now, let's take that sharp turn you mentioned, Microsoft and Majorana 1.
Right. A completely different philosophy. Topological quantum computing.
They're trying to build qubits that are naturally resistant to errors, using these things called Majorana zero modes, or MZMs.
Exactly. Microsoft's been pouring resources into this idea for, almost 2 decades now? It's a long-term bet. And Majorana 1 is the first hardware designed specifically to try and realize this.
So instead of building pretty good qubits and then correcting the errors like Google,
Microsoft wants to build qubits that are intrinsically protected from noise at the physical level because of their fundamental properties.
Okay, explain the theory. Topological qubits, Majorana zero modes. How does that work?
So conventional qubits, like Google's transmons, store information locally. Think of electron spin, up or down. That makes them vulnerable to local disturbances, stray fields, heat, whatever.
Right, noise.
Topological qubits aim to store information non-locally. The idea comes from topology in map properties that don't change when you smoothly deform something. Think of a coffee mug and a donut being topologically the same because they both have one hole.
Okay. How does that apply to qubits?
The hope is to encode quantum information in these global topological properties of a specially engineered material system. So a small local jiggle or defect wouldn't disturb the stored information because it depends on the overall structure, the shape of the quantum state, if you like.
And Majoranas are the key ingredient.
They are the proposed candidate, yes. Majorana zero modes. These are exotic quasi-particles, not fundamental particles like electrons, but collected excitations in a material that are predicted to exist at the boundaries of certain materials called topological superconductors. They have this weird property of being their own antiparticle.
First theorized way back in the 30s, right? By Ettore Majorana.
That's him. The theory says if you can create a pair of these MZMs and keep them physically separated, say at the two ends of a special nanowire, they can define a qubit. The state of the qubit, 0 or 1, depends on the combined electron parity of the pair, basically, whether there's an even or odd number of electrons shared between them. Because the information is encoded non-locally across the separated MCMs, it should be immune to local noise sources hitting just one end.
Theoretically invisible to local errors.
That's the promise. And if it works, the advantages are potentially huge. Inherent error resilience means you'd need much less overhead for quantum error correction. Maybe simpler designs, faster operations, easier scaling.
It sounds like a magic bullet almost, a high-risk, high-reward strategy.
Absolutely. If they can pull it off, it could leapfrog other technologies.
Yeah.
But the if is enormous.
So let's look at the hardware. Majorana 1, what is it exactly?
It's Microsoft's first chip designed around this idea. The ultimate goal for this design generation is 8 topological qubits. But the experiments they've posed so far are really focused on demonstrating the building blocks and measurement techniques on components.
And the special material they use.
That's the topo conductor. It's a complex heterostructure, basically layers of an indium arsenide semiconductor and an aluminum superconductor, grown with incredible precision, almost atom by atom.
And nanowires made from this stuff are supposed to host the Majoranas.
Under the right conditions, yes.
Yeah.
Cryogenic temperatures, specific magnetic fields. The theory predicts these nanowires should become topological superconductors, and MZMs should appear at the ends.
And how do they propose to make a qubit out of this, the tetron?
Right, the tetron is their proposed qubit design. It involves 4 MZMs, 2 at the ends of one nanowire, 2 at the ends of a parallel nanowire, and the wires are connected by a piece of normal, non-topological superconductor. That 4 Majorana structure is meant to be one qubit.
4 Majoranas for one qubit. Okay. And what did they actually claim to achieve experimentally?
The main claim in their recent Nature paper revolves around measuring the state of these potential MZMs. They connect the end of a nanowire, where an MZM is supposed to be, to a quantum dot.
A tiny electronic component.
Yeah. The idea is that the presence or absence of the MZM changes the quantum capacitance of the dot, how it stores charge, and they can detect that change using microwave reflectometry, basically bouncing microwave signals off it.
So they think they can see if an MZM is there or not?
They claim they can measure the parity associated with it, and they reported some numbers. Single-shot readout with about 1% error, stability against parity flips for roughly a millisecond, and they claim they can configure the setup to measure different properties related to the potential qubit state.
Okay. Sounds promising on the surface.
It does sound interesting, yes. They're clearly seeing something happening at the ends of these wires under specific conditions.
However, and this is a big however, isn't it? There's been quite a bit of controversy and skepticism.
Yes, there has. And it stems largely from a noticeable gap between the very strong claims made in Microsoft's press releases and blog posts and the much more cautious language used in the actual peer-reviewed Nature paper.
What's the difference?
Well, the press materials talked about the first QPU powered by a topological core and peer-reviewed confirmation of Majorana particles. Pretty definitive stuff.
Right?
But the Nature paper itself explicitly states that their measurements, while consistent with MZMs, do not definitively confirm their topological nature. And Nature even added an editor's note reinforcing that the topological nature wasn't proven.
That's quite a disconnect.
It is. And you have to remember the history here. There was a previous high-profile Nature paper back in 2018 from a related group involving Microsoft researchers that also claimed strong evidence for MZMs, which was later retracted due to flaws in the data analysis.
Right. That retraction definitely makes the community extra cautious. So what are the main scientific doubts this time?
The core issue is reliably distinguishing true topologically protected Majorana zero modes from other, more mundane quantum states that can mimic some of their signatures. These are often called Andreev-bound states, or ABS.
Okay, so you can get signals that look like Majoranas but aren't. False positives.
Exactly. It's technically extremely challenging to create an experiment that unambiguously rules out these trivial ABS explanations. Many experts who've looked closely at the data presented in the Nature paper feel that it's still consistent with, or perhaps even better explained by, these non-topological Andreev states. The topological gap protocol they used to test it has also faced criticism regarding its interpretation.
So the jury is still very much out on whether they've actually got stable Majoranas.
Very much so. And Microsoft has acknowledged that the Nature paper reflects work submitted about a year prior, and their stronger, more recent claims, like having a functional qubit, are based on internal, unpublished data that hasn't gone through peer review yet.
Which, for claims this big, is a problem. You really need that independent validation.
Absolutely. Extraordinary claims require extraordinary peer-reviewed evidence.
So, bottom line on Majorana 1 right now, it's a research device showing some interesting measurement results on components of a potential qubit.
Specifically, on half of one proposed tetron qubit.
But it hasn't performed computations, hasn't demonstrated coherence times, and hasn't definitively proven the existence of the crucial topological states.
That seems a fair summary of the current publicly validated state. There's a significant gap between the ambitious vision and the confirmed scientific reality at this point.
Okay. But they do have a roadmap, a vision for scaling this, assuming they can solve the fundamental physics.
Yes, they do. The ultimate goal is still that million-qubit processor on a single chip. They've outlined a 4-generation plan based on the Tetron architecture.
What are the steps?
Gen 1 is basically demonstrating a single controllable qubit. Gen 2 is getting 2 qubits working and showing entanglement, using a technique called measurement-based braiding for gates. Gen 3 aims for an 8-qubit system capable of quantum error detection. And Gen 4 beyond is scaling up towards fault tolerance, using custom error-correcting codes they believe could be much more efficient, maybe 10x more efficient, than the surface codes Google is using.
10 times more efficient would be a game changer.
It absolutely would if the underlying topological qubits work as hoped and are stable enough. They're also part of a DARPA program aiming for a fault-tolerant prototype in years, not decades. It was, well, extremely ambitious given the current state.
It all hinges on getting past that first hurdle, right? Unambiguous proof of stable, controllable MZMs. And then the engineering challenges on top of that, fabricating these complex materials reliably, controlling them, dealing with things like quasi-particle poisoning that can mess up the states.
Exactly. It's a massive physics challenge first, followed by a massive engineering challenge. Much higher risk than the superconducting route, but again, the potential payoff is enormous if they crack it.
Okay, so let's try and compare these two paths directly then. Google's Willow, Microsoft's Majorana 1, fundamentally different philosophies.
Totally different. Google, take a known, relatively mature technology, superconducting transmons, except that they're noisy, and throw massive engineering effort and sophisticated error correction, surface codes, at the problem.
Yeah.
Build the best physical qubits you can, then fix the errors in software encoding.
And Willow shows that error correction part is actually starting to work as predicted.
Right. Their milestone demonstrates the principle. Microsoft. Pursue a revolutionary new type of qubit, topological, that is supposed to be intrinsically robust, naturally protected from noise by its physics. The philosophy is, engineer the errors out at the hardware level, drastically reducing the need for complex correction later.
But the big challenge there is actually creating and verifying those intrinsically robust qubits in the first place.
That's the crux of it. Maturity-wise, there's no contest right now. Superconducting qubits are decades ahead in terms of scale, control, demonstrating algorithms, testing QEC. We have 100-plus qubit processors. Topological qubits are still largely in the fundamental research phase, trying to nail down the basic physics. Some estimate a 20-30-year lag, though Microsoft hopes to close that gap much faster if they have a breakthrough.
And the scaling challenges look different too.
Completely. For Google, it's managing the sheer overhead of surface codes, needing potentially millions of high-quality physical qubits for thousands of logical ones. It's cryogenics, wiring, control complexity, minimizing correlated errors. Huge engineering. For Microsoft, the immediate hurdle is the science. Prove you have stable MZMs you can control. Then they face the challenges of fabricating these exotic materials at scale, making reliable qubits, etc.
So potential advantages. Google builds on existing tech. Proven QEC principles, incremental gains add up. Microsoft offers a potential shortcut to efficient fault tolerance if the physics works out.
Exactly. Engineering path versus physics breakthrough path. Willow definitely strengthens the case for the engineering path. Tangible progress is being made, but it highlights the immense scale required. Majorana 1 is the high-risk bet on a physics revolution that could rewrite the rules if it pays off. But the scientific risk is substantial.
And of course, there are other qubit types out there too. Trapped ions, photonics, neutral atoms. It's not just these two.
Definitely not. The field is incredibly dynamic. We might see hybrid approaches or another modality might leap ahead. It's still very early days.
Okay, let's summarize that comparison. Willow, superconducting transmons, surface code QEC, 100-plus qubit scale demonstrated. Key milestone is the below-threshold QEC. Mature tech, strengthened demonstrated QEC scaling challenges the massive overhead.
Right. Majorana 1, topological qubits, MZMs, aiming for inherent protection, low QEC overhead. Current scale is component-level research. Key milestone needed is definitive MZM proof and qubit function. Maturity is early research. Strength is revolutionary potential. Primary challenge is proving the fundamental physics.
Two very distinct bets on the future of quantum computing. Now, before we wrap up, there was one more slightly out there discussion that popped up after the Willow announcement, linking quantum computation to the many worlds interpretation. Parallel universes.
Ah, yes. That definitely stirred up some debate. Moving from physics and engineering into, well, philosophy of science almost.
So the idea Many Worlds, or MWI, says that when you make a quantum measurement, the universe doesn't just pick one outcome, right? It sort of splits. And all possibilities happen in separate, parallel universes.
That's the gist of it, yeah. Proposed by Hugh Everett. It avoids the tricky wave function collapse problem by saying the universal wave function just evolves smoothly, deterministically, but contains all these branching worlds that don't interact after splitting.
And David Deutsch, a big name in quantum computing theory, is a proponent of this. He thinks quantum computers somehow use these parallel universes.
He argues strongly that MWI is the only interpretation that makes sense of quantum mechanics, and yes, he suggests that the power of quantum computers comes from them performing calculations simultaneously across vast numbers of these parallel universes. The interference effects we use are, in his view, interactions between these worlds.
You can see the appeal, right? When a quantum computer does something seemingly impossible, like factoring huge numbers with Shor's algorithm or Willow's RCS result.
It feels like it must be tapping into some resource beyond our single universe. The superpositions, like existing in many worlds at once, interference is the worlds interacting. It provides an intuitive, if mind-bending, picture for the speed-up.
And Hartmut Neven from Google even referenced this, didn't he? Saying the huge classical simulation time for Willow's RCS kind of lends credence to the multiverse idea.
He did mention Deutsch's idea in that context, yeah. The sheer scale of the classical calculation makes you grasp for an explanation.
But, and here comes the counterargument, standard quantum mechanics explains all this perfectly well without needing parallel universes, doesn't it?
It absolutely does. The mathematical formalism of quantum mechanics, superposition, entanglement, unitary evolution, fully accounts for everything we observe in quantum computers, including the speedups for certain algorithms. MWI is just one interpretation of what that math means about reality. It's not required by the math itself.
So no experiment, including Willow's, can actually tell us if MWI is true or if another interpretation, like Copenhagen, is correct.
Nope. They are all consistent with the experimental results. Linking Willow's performance specifically to MWI is a philosophical choice, an interpretation layered on top of the science, not a scientific conclusion derived from the experiment.
And a lot of physicists push back against this linkage pretty hard.
Oh, yeah. You hear words like speculative, philosophical, misleading, even utter nonsense from some critics. The argument is that standard QM works fine, thank you very much. Some also argue that if computers really tapped infinite universes, maybe they could solve even harder problems, like NP-complete ones, efficiently, which most researchers believe they can't.
And there's a risk of confusing people, isn't there? Mixing solid engineering progress with very speculative interpretations.
Definitely. It can overshadow the genuine, hard-won scientific achievements like the QEC progress and misrepresent what the experiment actually demonstrates. It's important science communication.
So the deep question of what quantum mechanics really means about reality, that's still an open debate. Quantum computing experiments are pushing boundaries, but they aren't settling those foundational philosophical arguments.
Exactly. It's fascinating to think about, but we need to keep the experimental results distinct from the interpretations we might favor.
Okay, so bringing this all together then, what are the key takeaways from this deep dive into Willow and Majorana 1?
I think we've seen really significant engineering progress from Google with Willow. They've pushed superconducting qubits forward, and crucially, they've hit a major milestone validating the principles of surface code error correction. It makes the path to fault tolerance look more like a concrete, albeit massive, engineering challenge.
But highlights just how massive that scaling challenge really is.
For sure. And then on the other hand, Microsoft is taking this incredibly ambitious, high-risk shot with topological qubits. Majorana 1 shows they're making progress on the building blocks, but the fundamental scientific validation proving they actually have stable topological states is still missing from the public peer-reviewed record. If they succeed, it could be revolutionary, but the if remains very large.
So two very different strategies, both facing huge hurdles, and the future likely involves continued breakthroughs in both science and engineering, maybe from these groups, maybe from others.
Absolutely, and it's all driven by the incredible potential applications, isn't it?
Yeah.
Designing new materials, discovering drugs, breaking codes, maybe new AI. That's the carrot dangling at the end of these very long sticks.
So, maybe a final thought for you, the listener, to mull over. Reflecting on this, you have Google's steady engineering driven progress versus Microsoft's potentially game changing physics bet. Which approach do you find more compelling right now? Consider that balance between the results we can see today and the potential transformative impact down the road. It might also prompt you to dig a bit deeper into how quantum error correction actually works, or maybe even explore those different mind bending interpretations of quantum mechanics itself.